The sun has been one of our main sources of strength lately, and it is about to undergo an amazing transformation: the reversal of its magnetic field. This phenomena, which occurs periodically and primarily near the middle of the solar cycle, has profound effects on us here on Earth. Unbelievably, there's a chance that the sun could soon pose a severe threat to the world, one that could bring about total chaos and ruin for all living things. As you will discover, the solar dynamo, the movement of electrically charged gases inside the sun, is what generates the magnetic field. Over time, convective changes and the sun's transformations cause this magnetic field to become more complex and rearranged. Eventually, the north magnetic pole turns into the south magnetic pole and vice versa, resulting in a total reversal of the magnetic poles. Could we then dissect the entire cycle and examine the sun in greater detail? The sun is mostly composed of plasma, which is made up of hydrogen and helium atoms that are not attached to any other particles and are instead a mixture of free electrons and ions. The radiative zone and the convective zone surround the central region of the sun, which is separated into multiple layers. The most important region of the sun is its center, where nuclear fusion transforms hydrogen into helium and releases massive amounts of energy. The radiative zone, which is located above the core, is where radiation is used to move energy outward. Photons are absorbed and re-emitted by the solar plasma in this region, causing energy to travel slowly outward. The convective zone, which is the outermost layer of the sun's interior, is where convection transfers energy. Convective currents are produced when hot plasma rises toward the surface, cools, and then descends once more. The tachocline, a narrow layer situated between the radiative zone and the convective zone. In the convective zone are where the solar dynamo mechanism mostly functions. The sun's asymmetrical rotation and shear flows, which are crucial in generating the magnetic field, occur at the tachocline. It's fascinating to note that the sun does not rotate like a solid body, something you have probably never heard of. Instead, different regions of the sun rotate at different speeds. This is called differential rotation, with the equator rotating more quickly than the poles. The magnetic field is extended as a result of the differential rotation, stretching, and twisting of the magnetic field lines. The sun's magnetic field varies over the course of the solar cycle, which lasts around 11 years and ends with a reversal of the poles. This cycle, which has multiple stages, is powered by the solar dynamo. The sun is at a condition known as solar minimum at the start of the solar cycle, which is marked by few sunspots and little solar activity. Generally speaking, there is a distinct north and south magnetic pole, and the magnetic field is simple and bipolar. There are more sunspots as the cycle continues. The spike in magnetic activity from the sun's interior is linked to sunspots, which are areas of extremely high magnetic activity. Over time, these sunspots move toward the equator and emerge in pairs with opposite magnetic polarities. The sun achieves solar maximum, a time of peak activity with the highest frequency of sunspots, solar flares, and coronal mass ejections, CMEs, in the middle of the solar cycle. The constant twisting and shearing caused by differential rotation and convection causes the magnetic field to become incredibly twisted and complex. The magnetic field reorganizes when solar maximum diminishes. The global magnetic field progressively reverses its polarity, turning the north magnetic pole into the south magnetic pole and vice versa, as the rearranged and tangled magnetic field lines reunite. The advancement and reorganization of solar plasma movement zones aid in this cycle. The sun has a phase of decreased activity following the pole reversal, culminating in solar minimum. The cycle eventually comes to an end when the magnetic field realigns. We are currently in the solar maximum phase, and the magnetic field of the sun is ready to reverse. We can anticipate some activity from the sun during this phase, which could be just as fascinating as it is dangerous. But the reversal of the sun's magnetic field is a continual cycle rather than an unanticipated flip. The sun's magnetic field fluctuates over the course of the solar cycle. The magnetic field is currently at its most twisted and tangled condition. It will eventually tip and start to restructure itself, which will cause a flip. So, when will the magnetic field of the sun reverse? Scientists use a variety of tools and methods to track the magnetic activity of the sun. Powerful telescopes at observatories on Earth and in space enable the creation of finely detailed photographs of the sun's surface and sunspots. The sun's magnetic field is measured, along with variations over time, by devices such as the Solar Dynamics Observatory and the Solar and Heliospheric Observatory. An important sign of an approaching magnetic reversal is how sunspots behave during solar maximum. As one approaches the sun's equator, sunspots become more frequent and noticeable, indicating that the magnetic field is growing more unstable and ready to reverse. While we're talking about it, let's examine sunspots in more detail. Due to differential rotation, which occurs when the sun's equator rotates more quickly than its poles, the magnetic field lines on the sun get twisted and braided. The cooler, darker areas seen in sunspot photos are caused by these lines looping over the surface of the sun, which inhibits the convective transport of hot plasma from the sun's center. In addition to being fascinating solar phenomena, sunspots have the ability to occasionally release strong coronal mass ejections, CMEs, and solar flares. Large amounts of energy and charged particles are released into space by these occurrences. They can interfere with electricity grids, interfere with satellite communications, and endanger astronauts in orbit if they are aimed at Earth. Furthermore, higher solar activity can intensify auroras, but it can also increase upper atmosphere radiation levels. While we're talking about it, let's look at the distinction between coronal mass ejections, CMEs, and solar flares. Even though they are both enormous solar energy eruptions, they are very different from one another. Solar flares are brief, powerful radiation eruptions brought on by the magnetic energy released from sunspots. They emit a vast quantity of light and energy, frequently in the form of ultraviolet and X-ray radiation. Imagine them as massive explosion-like blasts of heat and light on the surface of the sun. CMEs, on the other hand, are massive bursts of magnetic fields and solar wind from the solar corona. Imagine them as enormous bubbles of gas and magnetic fields shooting into space. During a coronal mass ejection, billions of tons of solar particles are propelled into space at very high speeds. CMEs and solar flares are not the same, despite their relationship. While a solar flare can happen on its own, a CME might occasionally accompany a particularly strong solar flare. A solar flare does not always result in a CME. Risk-wise, they are related because solar flares can interfere with radio messages and navigation, and their high radiation content puts humans in space at serious risk. CMEs, however, have the potential to cause geomagnetic storms that interfere with satellite operations, electrical grids, and navigation systems. Although they can intensify auroras as well, they seriously jeopardize Earth's infrastructure and technology. Another thing to keep in mind is that the quantity of high radiation that reaches Earth rises with periods of increased solar activity. In particular, spacecraft such as satellites are susceptible to increased solar activity. The sun's charged particles have the power to destroy electronic parts, interfere with communications, and even change satellite orbits. Apart from damaging technology and infrastructure, what further dire consequences could befall the planet? The Earth's atmosphere is not directly affected by the sun's reversal of its magnetic field, but it may be impacted by changes in solar activity. Variations in solar radiation may have an impact on weather patterns and atmospheric conditions, according to some research. For instance, elevated solar activity may cause the Earth's atmosphere to slightly warm, which could exacerbate already occurring climate change. Could auroras be the only good thing that happens to us on Earth? The intensification of these amazing lights is arguably one of the most noticeable results of increased solar activity. The interaction of charged particles from the sun with Earth's magnetic field and atmosphere produces these natural light displays, also referred to as the northern and southern lights. Although we frequently read about them, aurora borealis lights are also visible at the South Pole. Auroras can be seen at lower latitudes and are more common during periods of high solar activity, providing spectacular nighttime displays. But in addition to the stunning auroras, if we are unprepared, there are also more worrisome parts of the sun's magnetic reversal that could happen. The possibility of geomagnetic storms is one of the main dangers connected to a reversal of the magnetic field. When Earth's magnetic field interacts with solar wind that is overloaded with charged particles, storms like this arise. In severe situations, they may result in extensive blackouts and harm. On September 1, 1859, in the morning, one such occasion took place. As he often did, astronomer Richard Carrington was using his telescope to study the sun, but what he witnessed that day would go down in history as the first solar storm ever observed. Carrington noticed a brilliant white light flash coming from a cluster of sunspots around 11:18 a.m. The greatest known geomagnetic storm began with this incident, which is now referred to as the Carrington event. Carrington witnessed a massive solar flare, which is a strong outburst of radiation resulting from the release of magnetic energy that had been stored in the sun's surrounding material. Due to the immense power of this flare, Earth was the target of a large coronal mass ejection, CME. In 17.6 hours, the CME arrived at Earth, an extremely short period of time given that the Sun is 93 million miles away. The CME caused an abnormally powerful geomagnetic storm to strike Earth's magnetosphere. The impact was rapid and wide-ranging, disrupting the Earth's magnetic field and creating underground currents. In addition, there were significant disruptions to the telegraph lines, which at the time formed the core of international communication. Electric shocks were given to operators, sparks erupted from telegraph machines, and some message stations even caught fire. Even after unplugging their batteries, operators may still send and receive messages due to the powerful induced currents. The spectacular aurora show was one of the Carrington event's most remarkable and noticeable aftereffects. The auroras were seen much beyond of the usual polar regions because they were so brilliant and extensive. People saw vivid colors illuminate the sky as far south as the Caribbean, Mexico, and Hawaii. People in the northeastern United States were able to read newspapers by the light of the auroras because they were so bright that they lighted up the night sky. It was said that the brightness woke up gold miners in the Rocky Mountains, who thought it was dawn and started preparing breakfast. People reported seeing shimmering and moving red, green, and purple hues in the sky as it approached the horizon. Imagine, now, if Earth were to be struck by a solar storm today with the same intensity as the Carrington event. There would be disastrous results. The reversal of the sun's magnetic field is a huge transition that occurs approximately every 11 years as part of the solar cycle. This solar dynamo-driven event might have far-reaching effects on Earth, possibly leading to upheaval and catastrophe. The flow of electrically charged gases inside the sun produces a complex magnetic field that finally flips its polarity. This is what causes the sun's magnetic field. The sun's core generates energy by nuclear fusion, and the majority of its material is plasma composed of hydrogen and helium. Through the radiative zone and subsequently convection in the outer layers, this energy is sent outward. The solar magnetic field is produced by the solar dynamo system, which functions in the tachocline and convective zone. The solar cycle is propelled by the sun's differential rotation, in which the equator rotates more quickly than the poles. This causes the magnetic field lines to extend and intensify. The sun is currently in its solar maximum stage, which is characterized by its greatest sunspot activity and solar flares. Solar flares and CMEs have the potential to interrupt satellite communications, power systems, and astronaut safety. To forecast the timing of magnetic field reversals, scientists keep an eye on the sun's magnetic activity and sunspot behavior. Due to entangled magnetic lines, sunspots can cause large energy releases known as solar flares and CMEs, which have varying effects on Earth. Massive volumes of solar particles are ejected into space by CMEs, not energy as in solar flares. While these events have the potential to intensify auroras, they also seriously jeopardize Earth's infrastructure and technology. The behavior of the sun is an intriguing example of how physics and natural events interact to impact not just our solar system but also earthly life. It is imperative that we comprehend the intricacies of solar activity, particularly given our continued dependence on technologies susceptible to solar events. Nuclear fusion, which turns hydrogen into helium and produces massive quantities of energy in the process, is how the sun produces energy. After passing through the sun's layers, this energy eventually reaches the surface and radiates outward into space. Solar flares, coronal mass ejections, and sunspots are just a few examples of the various ways that solar activity can appear. Sunspots are darker, colder regions of the sun's surface brought on by magnetic activity. The solar cycle, which is made up of roughly 11 years of high activity, known as solar maximum, and low activity, known as solar minimum, intervals, is the pattern that these variations in solar activity follow. There are more sunspots at solar maximum, which increases the frequency of solar flares and CMEs. Unexpected energy explosions known as solar flares can produce radiation in all electromagnetic spectrums, including ultraviolet and X-ray light. These powerful outbursts can interfere with radio communications and endanger astronauts in orbit. On the other hand, massive eruptions of solar wind and magnetic fields, known as CMEs, are launched into space after rising from the solar corona. When these ejections are aimed at Earth, they can produce geomagnetic storms that upset the planet's magnetic field, producing stunning auroras as well as perhaps causing technological disruptions. Solar activity has an impact on Earth's surface and atmosphere in addition to space. According to studies, changes in solar radiation may have an impact on climatic patterns and may even be a factor in weather anomalies. In talks about climate change, air warming is a significant element that can potentially result from increased solar activity. Furthermore, it is impossible to overstate the possibility of solar storms causing technological disruption. Navigation systems, satellite operations, and electricity grids might all be impacted by a strong geomagnetic storm. Monitoring solar activity and creating plans to lessen the impact on infrastructure are part of preparing for such disasters. In order to more accurately forecast when major solar events might take place, scientists are still investigating the magnetic field and cycles of the sun. A combination of space and ground-based observatories are used in this study to measure magnetic fields, track sunspots, and examine solar wind. As technology develops, so does our capacity to forecast solar activity, which is critical for safeguarding our technological infrastructure and assuring astronauts' safety during space exploration. The impact of the sun on Earth is becoming more and more evident as we study it. The sun is still a strong force in our solar system, as seen by the breathtaking aurora displays and the possible dangers associated with solar storms. Comprehending its cycles and behaviors contributes to our understanding of space science and improves our readiness for the effects of solar activity on contemporary life.